Hi everyone, my name is Cousin Kam. The topic I am going to present today is the Brownian motion and diffusion. The Brownian motion was first observed by the botanist Robert Brown in 1827, where when he put the pollen grain in the water, he observed the unpredictable zigzag motion of the pollen grains. And there seems to be no pattern for this motion at all. When we try to explain the Brownian motion by the usual law of classical mechanics, we by addressing the collisions of water molecules on the pollen grains, because the pollen grain have much larger mass, the collision can hardly have any effect on the pollen grain at all. Furthermore, because the collision is random, on average, we expect there will be no net effect from the collision. From this point of view, the Brownian motion is unexplainable. Now, the turning point comes from the argument from Einstein in 1905, where we also have to consider the microscopic forces arising from the thermal fluctuation of water molecules. It means that in the equation motions for the Brownian particles, we also have to, besides the usual Stokes friction present from the friction coefficient, when we also have to consider a fluctuating force that accounts for the stochastic effect from the collision of water molecules. In Brownian motion, there are two time scales to keep in mind. The first one is the tau r relaxation time, which accounts for the energy dissipation of the Brownian particles. Because in general there will be friction from the collisions, then the energy of the Brownian particle will be dissipated in a certain time scale, and it is exactly this time scale is exactly the relaxation time. The second time scale is the collision times, denoted by tau COL, and is a time between subsequent collisions. In general, the relaxation time is much larger than the collision times in order for the Brownian motion to be observed. There are two general viewpoints to analyze the Brownian motion. The first one is the particle approach, which use the Langevin equation, where the equation of motion, including the deterministic and the stochastic forces, are written down to analyze the motion. The second viewpoint utilizes the kinetic approach, which is based on the Maxwell equation, and finally derive the Fokker-Planck equation for the Brownian motion. And it is exactly the second viewpoint that will be our main focus in the presentation today. In order to derive the Fokker-Planck equation for the Brownian particles, the starting point is the Maxwell equation. The f here is the distribution function of the Brownian particles. It depends on the position r and the velocity c and the time t. The pf here, the pf is the probability density that a certain Brownian particle having velocity c changes to c prime in a time interval. And these two integral terms are actually the source terms. And one is the outgoing term and the other is the ingoing term, as can be seen from the exchange of the first two arguments in the PF. Now, if we carry out the change of variables, as we write c prime equals to c plus u, where u is the change of velocity, which we also call the jump size in velocity, we can, after some rearranging, we can write down the Maxwell equation into the simple form, where the left-hand side is the streaming term of the kinetic equation, and the left-hand side are the source terms. Where now we see that the integral is expressed in terms of u now. Typically, because the jump size is small, we can take expand the integral in U, and we get the following form, where the A1 and the A2 are called the first moment and second moment of the jump size, the velocity jump size respectively. The first moment, the A1, is given by the integral of probability density with the velocity divided by delta t, and it is the statistical average of the change of velocity in the time interval delta t. On the other hand, the A2 is given by the integral of probability density with the square of jump size divided by 3 delta t, and it accounts for the fluctuation in the velocity of the Brownian particles. Now, the A1, because it's the average change of velocity, is actually given by the deterministic, is actually the deterministic acceleration given by the the frictions coefficients from the Stokes forces present in the equation of motions, and it is given by the minus gamma c over m, where the gamma is the friction coefficient and the m is the mass of Brownian particles. Now the next step is to expand the second moment in term as a series expansion in the velocity, because the velocity of the Brownian particle in fact is actually quite small. Retaining only the first term, we finally arrive at the final form of Fokker-Planck equation for Brownian particles. As we can see, the first two terms are the streaming terms of the kinetic equation, and these two terms are the deterministic part of the kinetic equation, as they stand for the deterministic forces that are present in the system. While the final term here is is probability in nature, since it accounts for the stochastic effects coming from the collisions of the fluid molecules on the Brownian particles. The next step is to try to apply this equation in some simple cases. First, we consider a homogeneous distribution of Brownian particles, so the distribution function shall not depend on the position. And also, there will be no external force in this case. Under these conditions, the solution actually, we will actually get a stationary solutions. And this is quite expected because at long times, the diffusion will arise, but because the system is homogeneous, then there will be no diffusions, and the solution will be automatically independent of time. Having this in mind, the Fokker-Planck equation will be reduced to this very simple form, where the solution is given by Gaussian, where the big C here is a normalization constant. So the width can be easily seen to be given by the big gamma over 2m times the small gamma. On the other hand, we know that if a system is at equilibrium with a thermal bath, it should have Maxwellian velocity distribution, having the variance given by kBt over m. So these two approaches should give rise to the same result, and matching them gives the following important relations, where the left-hand side is the noise intensity, and the right-hand side is the friction coefficient. This is one of the example of the fluctuation dissipation relation, which states that whenever there's a dissipation mechanism in the medium, there will be noise fluctuations. And in fact, these two terms share the same origin, which is coming from the water molecules. And all this relation does is to reunifying the separate forces that are present in the Langevin equation. Next, we consider the system which is at equilibrium with the thermal bath and temperature T, and under the action of conservative forces, which means that the force now can be written as the minus gradient of a potential. Then we have the following form of equation. Using separation of variables, we can get the solution, which is given by the following form. And this is quite the expected form from statistical mechanics, since we know that the stationary solution should be given by the Boltzmann weight. And this shows that the Fokker-Beck approach is quite consistent with the statistical mechanics. Now we enter the long time regime of the Brownian motion, which is diffusion. For this to be possible, we have to consider an inhomogeneous system of Brownian particles. In this case, another time scale exists, the macroscopic inhomogeneity scale. It's the scale that drives, because of the inhomogeneity in the system, that drives the diffusive transport phenomenon. In general, it has to be much larger than the two time scales mentioned before. If we look at the system in short time scale, the Brownian particles will exhibit ballistic motion. They will be like tiny straight trajectories of the Brownian motions. But if we view it on a long time scale, more precisely, it will view the system at the time scale much larger than the relaxation time, then the system enter into the so-called diffusive regime. And we should describe the system by using the diffusion equation, which is given by this form, where the D here is the diffusion coefficient. The solution, again, is given by the Gaussian, and we can easily see that the mean square displacement is given by 6 dt, because it's in 3 dimensions. So finally, so in one component given to 2 dt, in 3 dimensions, it will be 6 dt. Now we try to derive the diffusion equation by using the master equation. So the approach is quite similar to what we did for the Fokker-Planck equation for Brownian particles, but our main character in the story has been changed to number density instead of distribution function. Now the kinetic equation has a similar form as before, where the A1 here is still the external force, the external acceleration, and the A2 here is still given by the same form, but because from the previous slide we know the mean square displacement is given by 6t, we can insert the delta r squared into this form, and finally we get A2 equals to 2 dt. Inserting these two expressions into the kinetic equation for number density gives the following form for the kinetic equation, where we see that if the external force is absent, it will reduce to the usual form of diffusion equations. This somehow suggests the probability nature of diffusion, because for the fact that only if we ignore the deterministic external force, that we can only get to the diffusion equation. Next, we derive the Einstein relation. For this, we imagine a bunch of suspended particles immersed in a fluid under the action of gravitational field. Then our external force will be given by mg. Then the diffusion equation will be given by this form. Now, if we consider steady state, where the flux is independent of time, then in the steady state, by also requiring that the flux be vanishing at infinity, it implies that the flux should be vanishing everywhere. And so the terms in the bracket here should equal to 0, which leads to the solution in the following form. Because we know that the gravitational field is conservative, we can apply the Fokker-Planck equation for conservative force. with the potential given by mg z. Then matching these two expressions give another example of fluctuation dissipation relation, which is the Einstein relation, where the left-hand side is a diffusion coefficient, and the right-hand side is the friction coefficient. In summary, we have derived the focal plane equation from Brownian motion and applied it to two simple cases. The first one is homogeneous Brownian particles, and the second one is the conservative forces, and obtain the fluctuation dissipation relation for Brownian motion. Also, we discussed the diffusion arising naturally from Brownian motion at long times. We use the method equation to derive the diffusion equation, and we see that only if the external force is absent does the diffusion equation arise. Finally, we obtain the Einstein relation through the focal plane equation through a simple physical situation. And this shows how useful and significant of the kinetic theory is in analyzing various transport phenomena. And this is the end of my presentation. Thank you.